So today's session will be on quantum machine learning, broadly quantum AI, because we will be covering quantum machine learning, deep learning, quantum natural language processing, and quantum reinforcement learning. After this session, you will have a complete idea of what quantum AI looks like, right? But before that, a little about me. So I'm a senior quantum machine learning engineer at BQP. Sorry, I changed it in the slides. Before slide. Uh, so BQP is a startup headquartered in New York, right? We have a Bangalore here in office. We have an office here in Bangalore, and we have a product BQ5 has already launched. So we are already using quantum computing in production. So if someone comes up to you and says quantum computing is all theoretical, it's not, right? And so that's all B2B, and like we are mostly focused on engineering simulation, so aerospace and all that part, defense and stuff. QRL. So I am the founder of QRL, and as the name suggests, it's completely about everything. Quantum reinforcement learning. We launched QRL QAI, which is a pip installable SDK, so you can just install it with it, pip install QRL QAI and just use it like any other SDK. There are quite a few versions, but the documentation is there, GitHub is there, and so QRL QAI offers a bunch of quantum computing environments. So the first one you see there is Blocksphere. In the basics, you may have got that covered. It's a representation of a quantum state. 1 qubit quantum states representation to view it, diagrammatically. The second one is for quantum compilation. So whatever program you have that cannot be directly run on a quantum computer, so you have to compile it in a way such that you can run it actually. Then you have probably distribution, expressibility, error, noise, a lot of things that QRL QAI offers. But it's just for whoever who is interested in quantum reinforcement learning. Let's come to today's agenda, what we are going to cover today, what we are going to do today. So I'll start with quantum computing. What are the different types of quantum computing? There's no one type of quantum computing, right? And then I'll talk about quantum computing applications. So obviously, today we'll be talking about quantum AI, but there are a whole lot of applications of quantum. And I'll just introduce them to you so you can pursue them, based on your interests. Then we'll go into quantum AI. We'll look at quantum SVM. SVM is obviously the most basic machine learning algorithm that most of people are familiar, and quantum SVM algorithm in quantum AI community is touted to be one of the first quantum AI algorithms to show an advantage. So that's why I'm covering quantum SVM. Then we look at quantum computer vision. So computer vision is a pretty popular topic, right? Most of people know what is classical computer vision. We look at the quantum counterpart of that. Then quantum NLP, generative AI is everywhere, but it obviously started from natural language processing. We look at the quantum counterpart of natural language processing, and I'll show you the ideas from quantum NLP that are yet not explored in the classical NLP and that are very unique to quantum mechanics. Then we'll go to quantum reinforcement learning. What is quantum reinforcement learning? Why it's important for you to get. And once that segment is done, you'll have a whole idea of what quantum AI looks like. So, what are the major sub-segments of quantum AI, right? After that, I'll talk about my research papers. So that's all the different, whatever different topics we cover for quantum AI, that's all the theory. But in the next segment, I'll show you my research, the actual research papers that have been published in quantum AI and how they have actually outperformed the classical AI, the classical AI counterparts, right? So that's the agenda today, and I hope this ends up being the best session for this entire weekly series. And when you walk out of this room, you have a way better idea of what is quantum AI. Okay, let's start with quantum computing. How did this idea start of quantum computing? It started with one single sentence said by Dr. Richard Feynman, and in his lectures on simulation of physics in 1982, where he said, if you really want to simulate nature, the computational system must be quantum mechanical, because the nature is inherently quantum. So these are his exact words. Nature is in classical gamut, and if you want to make a simulation of nature, you'd better make it quantum mechanical. This one sentence ignited this race of quantum computing, why people started exploring quantum computing, why companies got into quantum computing, and why today we are all here discussing quantum computing. So the credit goes to him. So I know basics of quantum computing are covered in the previous sessions, but I'll still cover them here for you. And I'll just cover the two major types of quantum computing. But first, what's quantum computation? So whenever someone says quantum computing, people generally picture that golden dilution fridge, right? And that's probably the first image that comes up in Google as well. But quantum computing is just not a quantum computer, right? Yes, one part of it is about doing computation or processing information with a quantum computer, but it's also about using the ideas and the math of quantum computing to solve problems. And this type of quantum computing, the algorithms that use that are called quantum-inspired algorithms. Not sure if you've heard about it, but such algorithms don't need quantum computer to run. They can scale with GPUs, right? And when I said, in the previous slides that my company QT has a Day-5 product and we are using quantum computing in production, we are using this type of quantum-inspired algorithm. So it's already in production, it's working. Okay, so that's the definition of quantum computer. So it's not just about quantum computer. That's what I really wanted to emphasize. It's about quantum computing and using the ideas of quantum computing. Two major types of quantum computing: the gate model, which is the most popular one that you might have seen. Other one is annealing based, and there's also third actually, the continuous variable, but it's much an initial state, so I just skipped it. So gate model is all about the quantum circuits and quantum gates that you might have already seen. And you generally use that one when you don't want to store and process more information, because it uses certain postulates of quantum mechanics that are very inherent to that type of quantum computing, right? And that's how the model actually works. Annealing is generally used when you have a solution and you want to get to when you already have one solution and want to transition to another. And this type of situation generally comes up in optimization. So you generally use this in optimization problem. So that was used. Now the big players. Now in gate model, actually there are many. I just listed IBM and Google's, but there are many players for gate model, and there is no one particular architecture. There are many types of architecture trying to explore and work on different aspects of this. Like IMQ is working for to achieve, because what they offer is all-to-all connectivity in qubits. That's their speciality, I would say, of that hardware. So it uses trapped ions. So you trap the ions in magnetic field and then use laser to manipulate them, their states. And then we have photonics and stuff to achieve quantum computing at room level temperatures. So But IBM and Google use superconducting qubits for their quantum computers. But yeah, so the gate model is actually a very big thing. But I just listed only two players. D-Wave is one of the biggest players in the annealing-based quantum computing, and that company has been around since 90s. So that company was started to build quantum computers before most of you were even born, and the company still exists right now, and it was one of the first companies to make a quantum computer on the planet, right? And okay, so if you come to SDK, you have Qiskit and Penny. Qiskit, I feel a lot of you might know because it's the first SDK people try out. The second one is Penny. So Penny is more of use for quantum machine learning, and that's why I listed it. Again, for annealing-based quantum computing, Ocean SDK, again, Ocean is created by D-Wave, and this SDK is generally used to solve optimization problems or graph problems, right? So this is a go-to SDK for that. Okay, the application, quantum AI and algorithm development, and this one's for optimization problems, as I told you. And again, this type of annealing-based quantum computing that's also being right now used in production, right? I see. Yeah.
I don't see how annealing is different from a gate. Is it a some part of this gate model?
No. So that actually is a different form of computation. So annealing-based quantum computers are completely different from gate-based ones, right? And this type of quantum computers, to make them is comparatively easier than the other one. That's why the first company, the D-Wave that I'm talking about, they started this because they knew this is comparatively easier to do as compared to the other one. Yeah. As I told you, right? Graph problems can be solved with it. I just told you. No. So annealing-based problems, they are optimization problems. So scheduling, routing, all such optimization. Again, graph can be treated as an optimization problem, right? Anything that you can bring down to optimization, even finance and stuff. Anything that you can bring down to optimization, mostly this can be applied, right? Okay. So we have a lot to cover. Let's go to the next one. Okay, very quickly, I'll just summarize the different applications, right? Today, we are obviously going to talk about quantum AI, but there's a whole lot of different stuff in quantum applications. The easiest one, is quantum software engineering. If you want to get into quantum computing in industry with a BTech, with a bachelor's degree, quantum software engineering is most likely, that's where your probability of success is highest, right? That's why I'm just listing example. Quantum chemistry, as I just showed you, the origin of quantum computing happened for this simulation of physics. So that's what quantum chemistry is. Then quantum cryptography, because that's a communication, and most of the governments and everyone is really focused on quantum cryptography. So if you want funding and stuff, it's easier to get if you are into cryptography. Quantum finance, JP Morgan is leading this quantum finance race. They have published a whole lot of stuff on quantum finance. Just check their work, and people are really serious about quantum finance because again, it promises speed ups. It proposes better optimization, and whenever money is associated, that gets important. Quantum communications, again, very important, and then the final one is quantum hardware. Hmm.
Where would computational physics fall in this?
Where would?
Computational physics, like ComSol is ComSol, like the software is ComSol for computational physics.
See, there is so quantum compilation and stuff would come into quantum software engineering because quantum computers are just not quantum computers, right? It's a complete stack. So there's an associated classical stack that's associated with it because even there's cloud associated to it, right? So whenever a quantum machine comes, the inputs are translated so that the quantum computer can actually take it in. The outputs are then, processed back. There's cloud that's going on. So even when you look at a quantum computer, when you want to scale, it's not just number of qubits you are scaling. The entire architecture needs to be scaled, and everything has to be very efficient. So quantum compilation and all the classical computation side of stuff would fall under quantum software engineering. So I just listed it quantum software engineering, but even inside that there would be many other things that you can try to have. Okay. Okay, get ready for math. Oh, we have overview first. Okay, let me give you an overview of the quantum AI landscape. So there are like many ways of bifurcating this, but I've done it this way. So the first part is the quantum machine learning part. In these type of algorithms, you will most likely see that there is already an existing classical machine learning algorithm, and what they're trying to do is use quantum computing and try to make that classical machine learning algorithm more efficient. So you try to use some ideas of math, or generally the math from quantum computing, you insert it in the existing classical machine learning algorithm and try to achieve a speed. That's the general basic mindset for quantum machine learning. Examples are quantum SVMs that you will see in detail, and then Q-means clustering, which is the quantum analog of K-means clustering, which is an unsupervised machine learning algorithm. Then we have also Q-boost and quantum Boltzmann. So why I have highlighted this in yellow and the other one in white? Because that is gate model quantum AI. This one is annealing based quantum AI. Right? The rest of the different other things what you are about to see, there are also gate model quantum AI, whatever I'm about to talk, the rest of this, it all will be gate model quantum AI because it's the most prominent AI right now. And if you take an internship or go for some work, most likely you will deal with gate model quantum. But quantum AI also exists for annealing. Just know that. So Q-boost, for example, is the quantum analog of XGBoost. It's a boosting algorithm, Q-boost. And quantum Boltzmann, if you know, we have Boltzmann machines in classical AI, right? So that's the quantum machine learning. Quantum deep learning, I just bifurcated in quantum computer vision and quantum NLP because those are the two things we are about to see today. But it can go, further than this, deeper than this. But we'll just stick to that. And quantum deep learning is the algorithms in quantum deep learning are much different from classical deep learning. So you'll see a lot of difference when you look at a quantum deep learning algorithm and try to look at its classical variant, right? Then we have quantum reinforcement learning, which is my favorite branch of AI, and that's so reinforcement learning. It's a framework where you have an agent that is placed inside a world, right? And what it does is it takes some action, it gets some reward from the environment. If the action is good, a positive reward. If the action is bad, negative reward. And with this, with this process, eventually agent learns. So it's pretty much how humans learn in life. They do their action. If it's positive, you get some good results in your life. If it's negative, you get some bad results in your life. eventually you understand what is right, what is wrong. Right? And in quantum reinforcement learning, again, there are two types of quantum reinforcement learning. So in the classical reinforcement learning, you have, as I told you, you have an environment, you have an agent. If you just switch one of those components, to be a quantum, say quantum environment or quantum agent, then that becomes quantum reinforcement learning. So if you remember the first slides, I showed you a bunch of different GIFs, right? They were all quantum environments. That was quantum reinforcement. Then you also have different quantum algorithms. So if you have a quantum envelope of a classical reinforcement learning algorithm, then even that would become quantum reinforcement learning. So either you change the component, agent or environment to be quantum, or you take an existing classical RL algorithm and use its quantum envelope. Right? Okay, less than so. Okay. So just to demonstrate, first, one machine learning what it is, right? We look at quantum SVMs, and as I told you, for the reasons that I just mentioned, that it's touted to be one of the first algorithms that could potentially show some speed up. So, yeah, so classical SVM system is a very old existing machine learning algorithm that's been there for a long time. Quantum SVM, obviously, is the quantum envelope. Okay. So what a quantum computer is good at? So one of the main things that a quantum computer can do is actually give you probabilities. Different states and the probability. This is it. Any doubts so far? Okay. So this is one of the things that quantum computer can do, right? It can give you probabilities of states. How can we use this in a support vector machine learning setting? Right? Support vector machine learning. Okay. Before that, what is kernel trick? Just to revise. So it so happens that support vector machines are generally used to classify data, right? So type 1 data, type 2 data. But it may happen that the data that is given to you is not linearly separated, right? So quantum SVM generally just linearly separates, classifies your data. But if you are given data and in the dimensional space that is given to you, it may not be linearly separable, right? So you use a kernel trick, and what you do is project it to a higher dimension and then try to use the support vector machines to classify the data in the higher dimension. That's kernel trick. Okay, so that's the visual representation. You can see in 2D, this is not linearly separable. With a single straight line, you cannot divide the red and the green points, right? Now, if I project it to 3D space, you can see now I can take a plane and divide the two types of data. That's kernel trick. Yes. So it could be as simple as from if you have just x, use x square, use x cube. As simple as that. Depends on your data. Okay. So the math stuff. This is not really important if you don't know. So this is basically the language that you will find that you actually use in support vector machine, and that part is not really important. What's important is that final dot product, the xj, vector that you've seen, only that much. Just remember that. Now I just told you, right, that we use kernel trick in order to map to a higher dimension the existing data, say from 2D to 3D, simple as that. So if you want to map, from a lower dimension to a higher dimension, you need a feature map, right? As I told them, it could be as simple as x squared, right? Just a square function mapping it from say 1D to 2D. Let phi be that feature map. So we can project from r to the power n to r to the power d, which is where obviously d is greater than n. So like n can be 2, d could be 3. So you are basically projecting from 2D space to 3D space. Now, what you see that's a kernel. So that dot product that you are seeing, what we are doing, we are just checking those points because obviously we are using kernel trick, right? So we are using the feature map on the 2 points, projecting it to a higher dimension space. Okay, so that's here. Yet it's all classical thing.
The maximized thing is just the Lagrangian. Is that?
Yeah. Okay. So I just repeat the same last line on the previous slide here. So that's still classical. And you know that's dot product, right? That's dot product. What you see in the line below, that's a quantum computing way of writing dot product. Yeah. So that's bracket notation. It's I hope the basics are covered. You know that. Now we are slightly changing the definition of feature map. We are bringing in quantum circuit into the play, right? So that this capital phi be a quantum circuit that creates this feature map state phi, the smaller phi, when it acts on the ket0 state. So ket0 is obviously the initial state, which is always we start with. So we have a quantum circuit when it takes an input x or like the data point, and it eventually produces a state which is the higher dimension space, right? So that's again in the bracket notation I just written there. So this is your quantum circuit acting on this, producing this final state, right? Say you have that quantum circuit. So now, based on that, you can see the dot product now is just having this circuit being applied on ket0, having the adjoint of that circuit applying to the Brazil, right? Now, what is that adjoint circuit? It's basically changing your circuit from right to left and inverting the case. And that's okay, If you use Penguin, it's just calling one function qml.adjoint. That's not a difficult part. So you can see how we use the dot product, the classical dot product. What we simply changed was from a classical dot product, we introduced the quantum dot product. That's it. And we just rewrote it. So we just assumed we have a quantum circuit that does the kernel trick, and we just keep it there. Okay, just rewriting it again. Okay, so when you apply that quantum circuit on ket0, you get some state, say S1, right? Now, you have that S1 state, and you apply the adjoint circuit, the adjoint variant of the original circuit on that ket S1, obviously, because if you just do the calculation, you will have that S1 state, and if you just resubstitute, you have S1 there. What you will do again, you have that circuit, apply it on S1 state. That's what it basically means. Now, so this is what your term is being reduced to, right? So the final state that you get after applying that phi dagger quantum circuit, that would be, say, let's x to some state. Now, if you know basics of quantum computing, whenever such term comes up, right, that basically means the probability of finding this state in this state. In quantum computing, when you end up with this, n of bracket square, this particular thing, what it actually means is that whatever state this is, what is the probability of finding this state to be this? That's it. So remember I told you quantum computers are good at probabilities. That's what it meant. Okay. So what happens is, say, if you run a quantum circuit, say there's one qubit, for example. So you have ket 0 and ket 1, two possible outcomes. So say you got 50-50% say, right? Then that 50%, the 0.5 will be the answer of this. Because the first index is the probability of the zeroth state always, right? When you run the quantum circuit of one qubit state, then you will have at the end a probability state vector of size 2. The first index is the number you actually need. So your entire kernel computation is just running a quantum circuit. Whatever probability state vector you have, just take the first value. So that's how you change the classical support vector machine to quantum support vector machine. Did you get that? Was that confusing? If it is, it's okay. But I don't want you to understand the whole thing whatsoever. What I want you to do actually is just understand how things are being done. What we simply did here, we took kernel computation, which is classically expensive. If your data is, depending on the size of your data, dimension of your data, that in that Lagrangian dual form, the rest of the stuff is simple. That kernel product is a difficult part. So what we did then, we took the dot product that was in the classical form. We simply did convert the classical dot product to quantum product. We already know that a quantum computer is good at giving probabilities. So what we cleverly did that we reduced the entire thing to finding a probability. Right? So we used two ideas. Where is classical machine learning struggling? It was the kernel dot product. Then the second idea was what is quantum computing good at? It's good at giving probabilities. So we used that. The two ideas that I want you to remember.
So we basically said that something we had to calculate manually, something the qubits will do for us, and we just have to check.
So So it was something that you do classically, the classical support vector machine, and depending on your data, that could be classically inefficient, right? So when you translate it to quantum, that gets much easier. So that was the basic idea. Right. Okay. And actually, I have a YouTube video on this on my YouTube channel, QRL, where I actually code the entire quantum SVM. So sklearn, if you have worked with machine learning, you may know sklearn, the scikit-learn package. You can actually create a quantum kernel directly, give it to a SVC class. It works with the classical SDK, right? Go check it out later today at home. Right. Okay, enough time on this. Okay. Again, points to remember: utilization of quantum computer for calculations, right? We brought in a quantum computer with its ability to give probability, and then use of quantum. So, quantum support vector machines are just about calculating the probability of measuring all zeros after preparing S. So, the entire quantum SVM algorithm can be summed up in this one sentence. Right? Okay. That was the only boring part, I promise. Right, now let's come to quantum computer vision. I'm sure a lot of people here would be exploring computer vision as a career, as a possible career choice, right? Let's revise it a little for people who might not be aware of it. This is classical AI, right? Classical computer vision. So what you do with, so this is a convolutional neural network. What you can do with the convolutional neural network, you can, for example, classify images. A very popular problem is you have, say, images of cats and dogs. Convolutional neural network can tell you in which image there is a cat and which image there is a dog, right? So this is the most fundamental thing you can do with a convolutional neural network. How it works? This is the image, pixel by pixel. You scan. This is a convolutional layer. We'll see what it is. You apply a series of convolutional layers, right, until you have a fully connected layer. So fully connected layer is just normal feed-forward neural network that you might have already seen. The convolutional layers I tell you, and why it is right. So consider that is the input image. This is one kernel. What it learns is the features of the image. So for example, if you have an image of a cat, it will learn what the face of a cat looks like. What are the features, what are the types of ears, how the eyes look like, right? The dog's eyes are like smaller. The eyes of a cat is wider, bigger. All those things will be learned here. And this is a spatially invariant algorithm. Before this, there were many image algorithms. But if you change the position of the object in the image, the algorithms would fail. That doesn't happen with this. Because you can see it is scanning patch by patch, right? So it's scanning this blue part of the image first, then it will shift by one column, scan the next part, and so on. And it will shift a row below, right? And it will scan the entire image, right? And it will figure out where the cat is, where the face of the cat is. So that's why this is a convolutional deep learning algorithm, and it is one of the most prominent deep learning algorithms, that led to a lot of great stuff that eventually followed. So this is a very important thing. Okay, welcome quantum computing into the picture. So the reason I explained all of that so that you understand what's going on here in this image. All the dark horizontal lines are qubits, obviously. It's a normal quantum circuit. The blue boxes that you are seeing are just quantum gates, 2-qubit quantum gates, for example. If you look, again, what we are trying to do here is we are taking nearby qubits and scanning it with quantum gates. So it's the same idea of classical convolutional networks that you are taking nearby pixels and scanning them with classical weights. Here, you are taking nearby qubits and then scanning them with your quantum weights. Again, so this is like the first convolutional layer, right? And then here is the pooling. So if you see in the previous image of the cat, the sizes was being reduced. If you see, the size keeps getting reduced as you go from left to right. The size starts getting reduced, and that happens because of max pooling. Basically, from a group of pixels, say 4x4 pixels, you take the max value. Right? So that's how you reduce the image. Similar idea here, right? So what they are using here is conditional measurement, right? Conditional measurement IBM supports. So how the logic works is that if the after the measurement, if the state is at 0, do this, otherwise do that. That's the logic, and that logic is being used here to reduce the size. So you can see here the number of qubits are just 4 as opposed to here 8, right? So we reduce the size of number of qubits using the conditional measurement. Again, later you have fully connected layers. So what I'm trying to do here is giving you an overview of what quantum computer vision looks like. If you go in the literature, there are 3 types of quantum computer vision algorithms you will see. This is type 1, a fully pure quantum convolutional neural network. Right? The entire thing is quantum. You can take the entire thing, run the entire thing on a quantum computer. Right? The final layer is fully connected layer, which is a variation quantum circuit. right? Then there are two other variations. The first is where you keep the rest of the architecture classical. So up till here, everything is classical. You just add a little quantum circuit at the end, and then you get these output. So this is a hybrid algorithm, and you'll see this a lot. And when I talk about my research, I will come back to this. So this is the second type of variation you will see, and I'll tell you why. Because you obviously know that we don't have a lot of qubits at our disposal, right? The quantum computers are still in the initial state; they are still developing. The number of qubits are less, and when you have, say, you're trying to classify with images. If you have 28 by 28 images, there are so many values, right? And you will have to downscale, but that would lead to lots of information, right? So they keep the classical part at the front so that there is no loss of information, and then they keep the quantum part. So that's type 2 variation. The final variation, if you may have already guessed, is the opposite. So you initially have quantum convolutional layers, and at the end you have the fully connected layers, the classical version at the end. Why? Because how a quantum layer learns is fundamentally different from a classical version. That's also one of the motto of my research. The way you introduce weights in a classical, any classical deep learning algorithm, that is fundamentally different from the quantum version. So these are the points you can remember. I don't want you to remember the math and stuff, that's not important. Remember these points, that the way a quantum layer, a variation quantum circuit to be more specific, the way that introduces weights or the trainable parameters, that is fundamentally completely different from how a classical layer would work. For example, the weights of this layer would be the number of connections going out by number of connections coming in. That would be the weight matrix for that classical layer. For a quantum layer, that would be number of qubits multiplied by number of layers applied. So that obviously is up to you how many layers you want to apply.
Is quantum convolution layers better for systems that are more quantum like right after the energy of a molecule or?
No. It works on classical as well.
Yeah, but it's better for quantum systems, quantum convolution.
As I told you, what people do is downsample the images. So if you have classical data and you still want to use this, downsample this, feed it by piece, maybe, right? You use such strategies, eventually make it learn. And as I told you, why people do this, right? The previous version was obvious that you have less qubits, so you use the classical version. That is very understandable. Why people do this is because the way a quantum kernel or a quantum convolutional layers learn, that is completely different. So the features that this thing can pick up, the classical version may not be able to, right? So you can pick up different features with this, and I'll talk about that more in my research. Okay. The most interesting part, I would say, quantum NLP. So NLP, I don't think I have to tell you, this is the age of AI, ChatGPT, and large models, and Anthropic just ships something new every day, right? If you have a very simple background in AI, you would still understand this. But obviously, I guess everyone here knows what is an LLM. LLM, everybody has slight test at least. A transformer, everybody knows what is a transformer. So this is the quantum version. So before transformers, we had LSTMs, long short-term memory networks. Before that, prior to that, we had recurrent neural network, and you have quantum versions of all of it. So directly taking a classical algorithm and using the quantum somewhere, right? So if you see, this is using a quantum transformer encoder, right? That uses a miniature quantum circuit there, in the inputs, right? In the LSTM cell. So this is one thing that people do in quantum NLP. Now I'm talking about what quantum NLP. What is the literature? And if you get into the literature of quantum NLP, what you'll see. This is the first type you will see. There will be an existing classical NLP algorithm like transformer or LSTM, RN. Even people have got quantum GPTs as well. You just go to GitHub, search for quantum GPTs, you will find quantum GPTs, right? So this is one type that you will see in literature if you pursue quantum NLP. The second one is much more interesting. This is core quantum NLP. What you are seeing is called a cupcake diagram. This is how you represent a sentence in a pure quantum way. Whatever those wires are doing, they are just showing the flow of information. You can take this, execute on a real quantum. And this diagram and how it works, there are many types of such diagrams. So these are called string diagrams. String diagrams, right? This is cupcake diagram, which is one type of it, the simplest one. But there are many ways how you can use these string diagrams. And this is a very core quantum way of representing a sentence, right? Now, what exactly quantum is it about? Now, this stems from actually categorical quantum mechanics. And the person you should follow if you want to pursue this quantum NLP, that would be Professor Bob. So he is the chief scientist at Quantinum. He just left it, I guess. And he is a professor of quantum physics at Oxford University. And he and his team at Quantinum also developed a pip installable SDK, which is Lambic, spelled as LAMBEQ. So that SDK is used to do this type of quantum NLP. So you can literally go right now, check out the documentation for Lambic, and you can literally get started with this type of quantum NLP. Now the reason for showing this was, I just want you to know that something of this sort exists, right? And this is a much less explored aspect of quantum NLP, right? So if anyone is interested in a career and in NLP, would like to do something really different, this is a great subject to explore. So this is what a pipeline sort of looks like, the quantum NLP pipeline. Okay, the final part. I hope the GIF is visible. This is what a typical reinforcement learning setup looks like, right? I told you there will be an agent, for example, neural network in our case. If you see, this is the environment here, and this comes from SDK created by OpenAI, the company behind ChatGPT. They created, before ChatGPT came, they had a framework called GIM, right? That GIM had multiple different environments. This is one of them. So what is the task here? What you're seeing is actually a rocket. And the task is make the rocket land between the two flags. That's the task of the student that it has to solve. So the rocket is landing, it has different parameters. Control it in a way such that it doesn't crash, and this is a lunar surface, which is on moon. It has the gravity and everything encoded for a moon's surface. And the goal is that make the rocket land successfully without crashing and between the two flags. This was created by OpenAI in 2016. And what I am creating, QRL, QAI, that I just showed you in the first few slides, that SDK is the quantum analog of this GEM framework. So this is the quantum variant that I'm creating for the GEM framework that OpenAI originally created in 2016. Right? So this is the setup. So you have your agent as a neural network, and will take some action, give it to environment. For example, here in this setup, you have this rocket, and it would maybe it would crash or it would land, whatever, depending on that, whether it is a good action or not. Just understand it that way. It will get some reward, right, and it will get the next state, right? And this is the loop, a very typical loop for reinforcement learning. What you see above, that's a sort of quantum neural network. That's what a quantum neural network may look like. And I have a video on my YouTube channel. It's an animated video for quantum neural networks. So people who are from AI may know 3 Blue 1 Brown. He's a very popular YouTuber, and he creates animated content for machine learning and deep learning. Using the same framework that he uses, I created using Manu, I created a quantum neural network video. It's a very popular video, but 42K plus views. That shows you the entire thing and an animation of from start to end how a quantum neural network works. But just understand that this is a very very simplistic version of a quantum neural network. So just note that here your agent has become quantum, right? If you remember in the beginning, I told you, if you change the agent or environment to quantum, you enter the domain of quantum reinforcement. This is what it is. So if you look at this is a block sphere environment. This is what QRL QAI offers as well. So if the basics are covered, you may know what is the block sphere. So what is the environment trying to do here? So you have a target state, which could be say ket plus state. You are starting from ket 0 state, and the goal of the agent is to figure out how to go from ket 0 to ket plus, which gates to use. It has got a set of gates, and it should be able to go from the target to the from the initial state to the target state. And I also got a newer version of this where it is mapped to a graph problem, right? But the agent does figure out eventually. And in my QRL SDK, you can actually see agent actually figures out that you need to use header mart gate to go from ket 0 to ket plus, and many such examples. Right? So this is a quantum reinforcement learning setup. Okay, so the boring part is done. So now you will see what quantum AI actually looks in the wild, right? So my research. Okay. A lot of you don't know this type of machine learning, which is physics-informed machine learning. But this type of machine learning is used at a lot of places, where money is concerned, like defense, aerospace. For these type of areas, this type of machine learning is very, very, very important, right? Physics-informed neural networks or PINs. This is one type of algorithm in the physics-informed machine learning setup. What they actually do is they solve partial differential equations, right? Give it any partial differential equation. It doesn't require any data in most of the cases, and be able to solve that partial differential equation for you. And that thing is super important for a lot of people in the industry. Two types of problems. What problem? You are just solving the partial differential equation. You just find the solution. That is a power problem. In the inverse problem, what you do is you obviously find the solution, but you also find the true values of property constants involved in the partial differential equation. So, for example, the damping coefficient in this example I've taken in the slide. You don't have the actual true value of the damping coefficient, but that value is optimized over time with the network, right? and you actually find the true value of the damping coefficient. This requires little data. Without data, this might not be. And this is a very simple example actually. If you take this to higher levels, this gets super important. Because why? Because partial differential equations are everywhere, right? They are in finance, weather forecasting, aerospace, in defense, in designing, everywhere, right? So this type of framework, it's an irony that it's less popular, but this has immense applications, and this actually was this type of this branch of AI started in 2019. It's a very new branch of AI, right? Okay, moving on. So I talk about QA pin. So QA pin, so original pin was Lord wants to open. So original pin was physics-informed neural network. And the basic idea, like what is the basic difference between a neural network and a physics-informed neural network is you change the loss function. So in a normal neural network, for people who know it, a typical loss function is mean squared error or binary cross entropy, that sort of thing. In physics-informed neural network, your loss function literally becomes the PD you want to solve. So over training, your partial differential equation is satisfied, and that's how the model learns. So on the left, what you're seeing is the classical pin, the normal pin version. On the right, what you're seeing is the quantum assisted physics-informed neural network that I created. And this comes from a paper published in 2024, right? What has been done here? So if you compare the left and the right, the rest of the part is same. The only change is the quantum hidden layer, right? So what I've done here is, took the first hidden layer, replaced it with a variational quantum sum. That's it. But the obvious question is like, क्या मजा आया करके किया है, right? ऐसे करने के लिए कुछ भी करने का मतलब नहीं ना. So why we did this? What happened? Like how this helped actually? Now let's go back to the same point what I mentioned earlier. The way a quantum layer introduces weights is fundamentally different than how a classical layer introduces weights. So when I replace a classical hidden layer with a quantum hidden layer, it drastically reduces the weights. It makes the model lighter. But what also happens is it manages to learn better and give a better input representation to the layers that follow. So to explain neural networks, what happens is you give the input here, and what you get later, you are just changing the input representation of the initial input you received. What a quantum layer does is it gives you a better input representation. Why? Just as I mentioned, the weights, the way a quantum layer introduces weights is fundamentally different than a classical layer. So this was the paper 2024, and the QA pin reduced weights by 20% as compared with the classical version, and it was compared with classical pin and JAF pin. So JAF pin was a modified variant, state-of-the-art sort of pin back then, and QA pin managed to outperform both of them while having 20% less weights. These are the results from the paper. And you can see as you are increasing the number of qubits, the performance is sort of getting better. This is a scalable approach. It fits that. And the reason I'm showing this to you, it's not to flex my research, but it's to show you that quantum version of an AI algorithm can actually outperform its classical counterpart. QA pin outperformed the classical and the jar pin while having less widths, right? And again, this was like the Burgers equation, which is a non-linear PDE, but to instead consider it might be a simpler. Okay. What later? So that was the first step, and that was a forward problem. What we then did was solve this messed up looking PDE with QFA, right? And this work was in collaboration with Georgia Tech. So specifically with Dr. Prakash Jain's group. No, Suhas Jain. I got the last name right. So Dr. Jain's team came up with the PDE, and the problem here is that the Thomson coefficient mu, there is no classical way of finding its value, right? For this PDE, and it's a aerospace related problem, just understand it that way. There is no proper classical method of finding the value of mu. That's where QFN came, right? And so this was an inverse problem. So we solved for phi, obviously. We were solving the PDE, but we also found the value for mu. So the previous problem was a forward problem, the Burgers equation, right? And this one, the Stephen Studio ACDI equation. This is what the results look like. This is ice nucleation growth, to be honest. So how the ice grows in water. And this is a very important problem for aerospace, right? For detecting failures, and for when there's change in climatic conditions, and in such scenarios, this becomes really important. So the first row that you're seeing is analytical series. That we did with the true normal numerical methods. C pin is actually the normal classical pin. You can see how its solution looks like, and then later you have QA pin, which it may not be visible from this diagram, but it actually outperformed the classical pin. And note that this time around it had 32% less weights than the classical pin. So in the previous paper I showed you, the weights were reduced by 20%. This one had reduction by 32%. Right? And this was the second paper, and there's a lot of work that has been done to it, but we haven't publicly discussed it, so I'll end it here. Yeah, questions. And not just about questions about the session or the topics related to this particular session. Questions about quantum computing in general. Anything. Literally ask me anything, session.
We still need a very large number of qubits to run any algorithm, because right now we can brute force with the number of normal bits we have for those things. How long do you think it will take for our qubit capability to increase so that quantum is available?
Okay, so you're not talking about only with respect to quantum AI, it's a general quantum computing question.
Yeah.
See, as I told you, there are many players. A lot of them are doing a lot of great work. And yes, it's taking time, but things can progress pretty fast. In the last 12 months, I would say, the progress has been tremendous. Why? Because of the rise of AI. AI is being used to develop qubits. Let's see, the problem with qubits right now is it's noisy, right? So you run a quantum circuit, and the meaning of the gates changes. That's basically how you can understand it. That's a very big problem, right? What AI can do is, try to undo that error, sort of think it that way. It's a big field for error correction, but that's where AI is being used, and that's a very fundamental problem. Error correction and noise in the qubits. as I told you, scalability is a problem. Why? Because you don't have to just increase the number of qubits. It's the entire infrastructure that you have to scale up. So that's a problem, yes, but things are going well, I would say. Last 12 months, the progress has been really good. And obviously, no one can predict a very direct number that, in 5 years, this would be done. So, but it's going pretty well. And there's always a way around, if you really want to. So, what you talked about, quantum-inspired algorithms, that's a turnaround for it, right? That you don't have quantum computers, fine, it will work with GPUs. It really yeah. Yeah. So for photonics, the number one company is Shannon. And the Penguin SDK I showed you, that was for quantum AI, it's Shannon that is created. And if you remember, I discussed continuous variable quantum computing, that there is a third type of quantum computing, continuous variable, that is also being done by Shannon. Now, what is the difference? So, from the basics, you may know what is a qubit, right? It's a quantum analog of bit. That's not true for continuous variable quantum. There it's cube mode. It's different. Yeah, whole separate. Yeah. And that actually, how it's helpful, the photonics, it works on room temperature. That's the key, feature of it. The rest of the stuff, Google, IBM, and all superconducting qubits, you have to maintain a very low temperature. Yeah, almost at the temperature of space, deep space, that temperature. That's being sort of targeted with photonics. And yeah, people are doing, again, there are challenges that if you try out, doing quantum AI with photonics, you'll mostly see that you won't be able to use more than one independent feature. It's not able to, take the two features and correlate it and all of that. That's the problems are there. But photonics is where the key idea is just that can I do this at room temperature? Because if it can, then it opens a whole lot of different opportunities. If you can have a quantum computer and just keep it in a room and do computation, that is very promising. The problem is, as I told you, to make it work together. That's the problem. When I'm running a quantum circuit, there are multiple qubits. I'm having multiple gates, right? 2 qubit gates, 3 qubit gates, even multi-qubit gates. When I apply them, it should work well, right? That's a little problem that photonics is facing. Quantum machine learning in particular forms of it. That's a little problem. Anyone here who actually wishes to pursue quantum computing as a career? Okay.
I'm sorry, but maybe not QML because I'm letting you do it. I know practically nothing about it. And
okay.
It's just very overwhelming for me.
Okay.
Maybe at some point in my career, but I don't see it happening. I'm still thinking about it, but realistically, I see myself going into quantum computing for my career.
Okay.
But maybe towards computational physics. That's why the question is started. Seminar. That's why I asked.
Yeah. Anybody else?
I would love to succeed, but I don't have the ability to take the exam.
Okay. See, I'll tell you a key recipe of how you can pursue quantum while being risk-free. What he mentioned here, risk there. Quantum, any field of quantum, you will see that is, it comes with a classical counterpart, right? So, for example, the simplest thing, quantum software engineering. It is based on software engineering, right? Quantum AI, it's based on classical AI. You don't know classical AI, you can't do quantum. So, what you can do is, say if you want to do quantum cryptography or any quantum field, learn the classical version first. Even if quantum doesn't work, you have the classical part, right? That will still work, right? So that's how you can sort of try to play risk-free. So quantum machine learning, even if you think quantum machine learning may not work, machine learning already works, right? So that's how you can try to counter. Even if quantum software may not work out, but if you know the software engineering and AI doesn't take your job, then it will still work out fine, right? Your career will be still fine. So that's how you should try to tackle it, and that's how I tried to tackle it. The session was all good and okay. I talked about quantum AI and all this stuff, but I want to tell you that please pursue quantum. We need a lot of people involved, especially quantum AI. And it looks like, okay, quantum AI is a very difficult field, maybe, or it may not have a lot of scope, but it's a very interesting. Right? It's a field that requires a lot of people, right? A lot of intelligence. And at first, quantum computing can seem a little daunting. That it is difficult. Yeah, it's okay. It is difficult for everyone. But once you start going through it multiple times, a few times, right? It will feel a little easier. You will start being able to do things, and don't just sit and study things. Start implementing things. That's what I would say. And that's how I pursued quantum AI. So a bit about myself to inspire you guys to pursue quantum AI if I can. I started my career in quantum AI with a weekend, right? And yeah, I did quantum mechanics since I was 16, right? I knew quantum physics and stuff. Quantum computing I already knew before I entered engineering college, so I had that advantage. But later on, I learned AI. Later on, I learned quantum computing myself. There was no resources, right? I learned quantum AI myself, and the skepticism back then was much more than what it is right now. But I still took that risk because I felt I'd be able to do something for the sake. Right? Don't analyze if the subject is good enough for you. Just analyze yourself, are you good enough for the subject? If you can, whenever I go for a talk, I have given talks at IIT Delhi, IIT Jodhpur, IIT Guwahati, so many other IITs, NITs, right? Everywhere, wherever I go, I always say this one thing. Your value as a professional depends on what you can offer to a subject and not what a subject can offer you. Whatever the subject may be, if you can do good work there, you will be valued there, right? Software engineering is a very high-paying field, but if you are not good at it, then what's the point? You won't be paid. Whatever your subject is, if you are good at it, you will be paid well. Don't worry about it. With that, I conclude the session. I hope I was able to inspire you guys to pursue quantum computing, quantum AI, and you can reach out to me on LinkedIn. If you have any doubts, any questions, your organizing team is here. If you want to contact me, you can contact them. And please, yeah.
Thanks a lot, sir. As you said, quantum doesn't have much resources, but I think your channel is one of the best resources I could ever access. I actually started learning quantum from Sir's channel. I think he was really humble not mentioning it. I don't know if he mentioned it right. Sadly, for some work in the lab, I had to stay back. I couldn't attend the lecture. I hope all of you enjoyed it. All of you learned a lot. Yeah, we are very honored to have Sir, and I think we would like to thank him once again by. And we would like to give something from PS side, thank you for his side. So, sir. I am really out of breath. There was a lot of delay in the talk also, so there was some issues with sorting out the streaming platform and everything, and I guess a lot of people had left because of that also. We really apologize for that, for not providing a good enough crowd for you to speak after you have talked in such reputed places. I think at least they take away a message good enough to compensate for that. At least I did without attending the talk. Whatever interaction I've had with you, I think it was really beautiful. Yeah, that is all. So thanks a lot. Thanks a lot for your support. I would like to say personally, sir, I think you coming to this lecture kind of, adds up a lot, because this technically is my last year as the club head for this club, and I've been trying to get you from the first year, sir, and finally that you're here, I think it fulfills the whole cycle, and I feel really happy and fulfilled that you were here, sir. Thanks a lot, sir. Yeah, guys, if you have any questions, feel free to ask right now, or you can message Sir's contact if you need. I think, as Sir said, you can contact him through LinkedIn, and Sir is active in a lot of quantum communities like DARK, the QB Quantum, any other communities also. So I also wanted to ask, would you be ready to join the Q4S quantum community if you are okay with it? I'll add you into it. We have a small community; it's only for PS. Yeah, sure. So he'll be on that community as well. So you guys can ask him. Don't disturb him, obviously. Don't pester him asking for internships like typical PES students. Let him live. If you have actual doubts regarding quantum ML, quantum AI, please do ask regarding his library, anything. You guys can ask. Yes. I'm talking about not asking about the internship because I did. That was the first message I said.